Hey guys, Spency here. Today we are going to discuss a specific type of analysis called combustion analysis. Now, as chemical engineers, combustion plays a pivotal role in our lives, especially since it is a source of energy. Usually we combust organic compounds. Now, we define combustion as the chemical reaction that produces heat and light, usually in the form of fire. But before we proceed, let us consider some fundamental concepts. Complete combustion is the reaction in which a compound is completely turned into carbon dioxide and water. Theoretical oxygen, on the other hand, is the amount of oxygen required for the said complete combustion of the compound. Now let's consider the combustion reactions shown here. We are asked to determine the theoretical oxygen needed to combust 100 moles of methane. Now let's recall that the theoretical oxygen is the amount of oxygen required for complete combustion. Now, which of these two are the complete combustion reactions? If you answer the second one, you're wrong. Dun dun dun. Go previously in the video to determine where did you go wrong. If you answered the first equation, very good, you got it right. And thus, we can now say that stoichiometrically, the answer is 200 moles. We also consider the concept of excess. Excess is the amount of oxygen left if we consider complete combustion. Mathematically, it is expressed as actual minus theoretical. Percent excess, on the other hand, is the excess percentage with respect to the theoretical oxygen. Now, it is expressed as these three equations. It could be either excess over theoretical, or actual minus theoretical all over theoretical, or actual over theoretical minus 1. Either way, it would give you the same answer. Now let's revert back to our previous problem, wherein we're given these two equations and 100 moles of methane needed to be combusted. Determine the percent excess if 350 moles of oxygen is supplied. Now let's just use equation 3. And again, theoretically, we have 200 moles of oxygen. So that's 350 over 200 minus 1, that's 75%. Please note that your oxygen supply usually comes from air, which contains 21% of oxygen, since pure oxygen is reactive and very expensive. Now, after combustion, the substances come out as flue gas. We could analyze this flue gas through an ORSAT apparatus. An ORSAT apparatus is an instrument that contains certain chemicals that absorb certain compositions of your flue gas. What's shown here is a complete diagram of your ORSAT analysis. So your flue gas enters here before pyrogalol, which absorbs your oxygen. Then your KOH absorbs CO2. Then your sulfuric acid absorbs your organic material, your hydrocarbons rather. Your CuCl2 absorbs your carbon monoxide. Your palladium black absorbs your hydrogen gas. Your lead acetate absorbs sulfur hydride, and lead oxide absorbs your sulfur dioxide. Now, your nitrogen here is not absorbed by any of the compounds, so usually the remaining volume is your nitrogen. Please note that an ORSAT analysis is done on a dry basis, so we assume that water is condensed prior to this analysis. Now let's consider this problem. Propene gas at 32 degrees Fahrenheit enters a combustion chamber. The flue gas at 70 degrees Fahrenheit flows from chamber to a condenser, which condenses all the water. Part of the flue gas then enters an ORSAT apparatus where it gave the following report, which is prescribed on the table below. If the pressure of the process is 14.7 ChE or gauge pressure, determine the volume of feed required, the mass of water condensed, and the percent excess of air if we are to produce a gallon of dry flue gas. Now, once again, let's go to our calculation chamber and solve this. Hello guys, welcome back to the calculation chamber. And we are here to solve a combustion chemical engineering problem. So I printed out the ORSAT analysis for everyone's ease of viewment. So first things first, we have to draw a certain diagram. So we know that the feed here, propene, enters a combustion chamber. Then the gas enters a condenser, which separates the H2O. Then our flue gas enters the ORSAT analyzer. which gave the report here. So we know that only part of the flue gas went here. We know that some part actually went out. So the initial volume is only 100 ml. Although that we know that the flue gas here is approximately 1 gallon. So first let's determine the compositions of each. So we know that the difference between the initial volume and after pyrogalol is whatever is absorbed by pyrogalol, which is O2. So we just 100 minus 81.9011, then we divide by 100. So we could get approximately 18 point, I'm gonna round it off to 18.1%. Then we're going to do the same for sulfuric acid for CuCl2 and for KOH. So I'm not going to do that anymore, but more or less here is what's going to come out. So that's approximately after sulfuric acid, which absorbs your hydrocarbons, you will get 0.47% of C3H6. Then you're going to get one after CuCl2, which is your CO levels, 0.35% of CO. Then you're going to have 76% of CO2. Then you're going to have 79.3% of N2, which is given by this composition. Now that we have this, we have to determine the number of moles. Now we are given the conditions, so that's 2 multiplied by the number of gallons, 3.78, or that's the number of liters rather. Then we use ideal gas law. Then we convert 70 degrees, 7 degrees Fahrenheit into Kelvin. Thus we have 313.53 moles of gas. Now we could change this into moles so that we know that there is approximately 1.47 moles of C3H6, 5.51 moles of CO2, 1.1 moles of CO. Then you have 56.75 moles of O2, and you have 248.7 moles of N2. Now, next I'm going to use extent of reaction to determine the extents of the two reactions. So we have two reactions for this. We have 2C3H6 plus 9O2. I'm going to do them as balanced. 6CO2 plus 6H2O. So I'll label this as extent 1. Then I have C3H6 plus 3O2 produces 3CO plus 3H2O. I'll label this as extent 2. Now we know that extent 1 could be derived from CO2 and extent 2 can be derived from CO. So let's just do that. So extent 1 is approximately the amount of CO, which is 5.51, we then divide by its stoichiometric coefficient, wherein we will get approximately 0.92. Our second extent is approximately 1.1 divided by 3, which is 0.37. So we have now our two extents. We could calculate for NH2O, which is approximately 6E1 plus 3E2. We could get a final answer of, let's do that, 6 times 5.5 times 0.92 plus 3 times 0.37. We would get 6.63 mole. 6.63 moles, or if we change that to pound moles, to to pounds rather, pound mass, we have 2.618 times 10 to the negative 4 pound mass. I'm not going to show in this video on how I got it, but this is more or less the result. Now, I'm going to use another paper to calculate for the amount of gallons of propene needed. So we know that propene, what the propene went out with a value of 1.47. So that's 1.47 is equal to the propene out, the propene in, plus, minus, since it's a reactant, 2 E1 plus E2. Thus, our propene in is approximately 3.673 moles. Using ideal gas law at conditions 2 atm and at conditions 2 atm and 30 degrees Fahrenheit, you would get number of liters is 0.04116 liters. Now, afterwards, we could get the number of gallons, which is 0.010874 gallons. And that is our answer for the number of gallons required. Last, we're supposed to determine the number of excess. So we know that the actual O2 can just be derived from your N2, right? Because your N2, your actual O2 is equal to 248.7 moles of N2 times 21, just the molar fraction of O2 divided by 79, the molar fraction of N2. More or less, you could get 248.7 times 21 divided by 79. You're going to get 66.11. And theoretical O2 is complete combustion of your propene. So that's just using stoichiometry. That's just E1 multiplied by 9, which is approximately, I used that wrong. So I'm going to use basic stoichiometry in solving for this one. So I'm going to get the moles of propene, 673, then we multiply it by 9, then we divide it by 2. This is just using basic stoichiometry, so 3.673 divided by 2, multiplied by 9. We will get 16.5285 moles. Then we'll just use our equation, 66.11 divided by 16.5285 minus 1. We get more or less. So I'll put here excess is equal to 66.11 divided by 16.5 minus 1 is equal to 300%. So that's it. We basically solved a combustion chemical engineering problem. So that was our video, guys. Thank you for watching. If you want to subscribe to our channel, you could do so with the logo above. And if you want to check out for more 101 videos, you could click on the video down below. Thank you for watching, guys, and good luck on your long exam.